In this section, we're going to look at representing vectors in a rectangular coordinate system. We're going to start off by introducing what's called a unit vector. And a unit vector is any vector whose length is equal to 1, or whose magnitude is equal to 1. And there are two very commonly used vectors below, drawn here. One of them is the unit vector that is on the positive x-axis, and the next one is the unit vector that's drawn on the positive y-axis. Now these are used so frequently that they're given names. So the vector that is along the positive x-axis, whose length is 1, is named I, and the vector who's on the positive y-axis is named J. You can write the vector just by using the letter I. This can also be written in what's called component form using not a parenthesis but this sharp bracket, and I would be equal to 1, 0, meaning we went over 1 in the x but we didn't move vertically. And the vector J can be written in component form by using 0, 1. Meaning you didn't move horizontally at all, but you just went up 1 unit. These vectors are important because we can take any vector we want and write them in a rectangular coordinate system. So if I start with a vector whose initial point is at the origin 0, 0, and whose terminal point, we'll just say generically, is at AB. So if I draw this vector, basically what I can do is I can write this vector in terms of I and j by thinking of A and B as scalar multiples. Remember, this distance from the origin out to here, the length of that is A. And the vertical distance here, this would be B. So what I know is that this vector that goes from 0 to the point AB is basically the sum of two other vectors, and that the first vector, which would be what we would consider the horizontal component, will be this vector right here, whose initial side is at 0, 0, whose terminal side is at A0. That vector's name would be AI, where A would be a scalar multiple of I. Remember, I only has a length of 1, so if we want something to have a length of A, it would just be A times I. We can also draw the vertical component of this vector by drawing from the terminal point of A. If I draw vertically, this vector is going to be B, J. Right? J having a magnitude of 1, B also a scalar multiple. We know that this vector from 0, 0 to AB is actually the sum of the vectors AI and BJ. Remember, if I want to add AI plus BJ and I want to show that addition geometrically, I would draw a vector from the initial point of AI to the terminal point of BJ. So this new vector will be AI plus BJ. In summary, if we have vector v, whose initial point is 0, 0, and whose terminal point is AB, that this can be represented by the expression v equals AI plus bj. And this is what we call a positional vector. A and B are called scalar components of v. A is also specifically the horizontal component, where B is the vertical component. And the AI plus the bj is called a linear combination of those vectors. To find the magnitude of that vector, we find that the same way we found the magnitude of our other vectors. It's going to be the square root of a squared plus b squared. Even if a vector does not have an initial point at the origin, so basically any vector can be shown to be equal to a position vector. Let's start by sketching a few vectors in a rectangular coordinate system. And it's extremely straightforward. We're going to start with this first vector in example 2, which is v equals 2I minus 5j. So I'm going to show how to add this the long way, and then we'll take the shortcut. Right? Because basically what's going on here, we've got the sum of two vectors. We have a difference, but it's the same thing as adding the opposite. We have 2I, which if I drew 2I, that would be in the positive direction on the x-axis, and it would be a length of 2. So that would be what my 2I, the vector 2I, looks like. Now, 5j would be a vector in the positive direction, right? In the positive direction on the y-axis, except it's negative 5j, so it's going to be in the negative direction. So I've drawn negative 5j, I've drawn positive 2I. We know the sum of those vectors is going to be the vector whose initial point is at the initial point of 2I and whose terminal point is going to be at the terminal point of 5j. So our new vector 2I minus 5j is going to be this vector right here, basically the sum of those two vectors. Now you don't need to draw those two vectors in order to draw your final vector. We can think of this almost like an ordered pair. If we use the notation 2, negative 5, it just means from the origin we're going to go to the right 2 and we're going to go down 5 and we're going to draw our vector. So I'm going to go over 2. I used a scale of 2 because these graphs are kind of small. I'm going to go down 5. Right, my horizontal component is 2I, my vertical component is negative 5j, and I just connect the origin to that terminal point. So again, I don't need to draw the horizontal and vertical components to draw a vector. To find the magnitude of v, it's pretty straightforward. Right, we know that the horizontal component is 2, or the horizontal distance, and the vertical distance is going to be 5. It's just going to be the square root of a squared plus b squared. So it's going to be the square root of 2 squared plus the square root of negative 5 squared, which would just be the square root of 29. Let's look at student practice 2. We know that the value of a is negative 1, which that's our horizontal component, so I would be going to the left 1. The vertical component is 6j, so I'm going to go up 6. And I'll use a scale of 1 for this problem because so that it'll fit. So I'm going to go up 1, 2, 3, 4, 5, 6, put my terminal point. Then I've drawn the vector from the origin to my terminal point, so this would be vector v. So to find the magnitude of v, take the square root of a squared, so a is negative 1, plus b squared, which is 6 squared. So we're going to get the square root of 37. So we talked about the fact that even if a vector, is not a position vector, in other words, its initial side is